All right. Okay, so hopefully this shouldn't take long. Hopefully half an hour, take a break, and then I'll do some super heterodyne questions, then we'll get out of here. Okay? So this is the second part of frequency modulation. So what we're going to take a look at is how non-linearities affect AM and FM signals. So just a brief discussion about how non-linearities affect AM and FM signals. You'll see that it doesn't affect FM, but AM it does, and then we'll talk about how to generate FM signals in general. Okay, so let's get on to, let's review what non-linearities are. So when you have a nonlinear device, okay, the purpose is to take, the signal itself and then add to it either some nonlinear effects. You can either take the signal and square it or take it to the power 3 and so on and so forth. So we have some nonlinear system. We have put, you put some input in, and the output, could be something like this, where it would take the input and then have some sort of gain A to it. You add the input squared, have some sort of gain B, and so on and so forth. So it totally depends on how you design this nonlinear device. Some people usually just have a squared term. Some people do use a cube sometimes, but usually the nonlinear device tries to square or multiply the two signals together so that you produce a squared term. Okay? So we're going to take a look at how this kind of system, when you feed an amplitude modulated wave into the system, or frequency modulated wave, let's see what actually happens when you take a look at the output. Okay, so we have some sort of modulated waveform, whether it's AM or FM, and then we know for a fact that the frequency components are going to be concentrated at plus minus, whatever the transmission bandwidth you'd need. That's centered by the carrier frequency. So remember, when you're modulating, you're shifting all your frequency components over where you have your carrier frequency, which is at the center, and then you have plus minus, whatever the transmission bandwidth would be. Okay. When you put it through a nonlinear system, what's going to happen is that if you remember, when you square the signal, you're performing convolution of frequency domain. So what's going to happen is that you're making your bandwidth twice as large. So as you start applying nonlinear, operations, then what's going to happen is that your frequency components will actually the width will actually become larger and larger, depending on how much of a squaring or how much of a power term that you apply to each of the components. Okay, so what you can do is, because you are increasing the width of the actual bandwidth of the signal, you could put a bandpass filter if you want that is centered around the carrier frequency that you are looking at, and then you want to make sure that the width of the signal or the width of the bandwidth is whatever is deemed by the transmission bandwidth. So you can certainly get rid of all of these, as you start, if you have this nonlinear system, you're going to start adding, components which are outside of this particular range. So you can add a bandpass filter if you want to actually get rid of those and just keep whatever you want. And that would be the cleaned output. Okay, so let's take a look at your AM signal. So this is just double sideband suppressed carrier for now, just to make things simple. In general, you can use amplitude modulation if you wish, but let's just take a look at double sideband suppressed carrier for now. Let's put it through this nonlinear system and let's see what it actually looks like. So when we put it through our nonlinear system, okay, so what's going to happen is that it'll take your signal, and then remember, this is equal to, the output, right, is going to be A of, so if this is, x of t coming in, the output would be x of t, and then plus b of x squared t, and then so on and so forth. Right, so that's what's happening here. So you take your original signal, which is just your double sideband suppressed carrier, and multiply by A, and then you add it with whatever the input is squared, so this would be m of t cos of omega ct squared, right? And then that's what you get, okay? And then this would be just m of t and then cos omega ct cubed, and so on and so forth, okay? Now how this works here, this expression here is very simple. So remember, this can be expressed as 1/2 plus 1/2 cos 2 omega ct, all right? So then if you multiply this by m of squared, that's what's happening here. So this gets transferred over to here, right? Because you're also multiplying by m of t. Okay? This here, right, if you do the cube, if you actually work it out, what you get is that this is equal to that. Right? So if you actually work it out. So what you can actually do is you can split cos cubed up into cos times cos squared. Okay, and this becomes cos of x, and then 1/2 plus 1/2 cos 2 of x. Okay? And then when you multiply this out, you're going to get double angle here, and then that becomes 1 and 3, and then that's what you get. So that could be represented like this, and then so on and so forth. Okay, so you can actually group this into different cosines. So if you take a look here, we can group this one and this one together, right? And then that's what you get over here. This one is by itself, so that goes over here, and so on and so forth. So I'm just basically grouping things together. So what's going to happen is that you have a bunch of, you have a summation of terms where you have, you have one where you're modulating by omega c, then you have one which is modulating by 2 omega c, and so on and so forth. So if you put a bandpass filter centered at the carrier frequency, because you want to get rid of these, you just want the original one by itself, right? So let's take a look at what happens when you put a bandpass filter. What will happen is that everything is going to filter out except for the one that's centered at omega c, which is what's happening over here. Okay, so this is your baseband, right? This is your baseband that is centered at plus minus FC because of this guy, and then you have one that's 2FC, and so on and so forth. All right, so if you apply a bandpass filter, what's going to happen is that you get rid of all these three, and then you're left with this one over here. Right, and that's what happens. So the important thing to note is that so these all go away, and then what you're left with is this. And then if you take a look here, this is my original, modulated signal. If I put it through some nonlinear device, the output is going to look like this instead. So you're going to have your cosine wave, and what's going to happen is that you have your message signal, and then you have your message signal cubed. So this is not equal to your original message, so there is unfortunately some distortion involved. So in general, if you put your amplitude modulated wave through a nonlinear system, the output will unfortunately be distorted. You actually don't get the original message signal modulated, you get the message signal plus some cubic term, which unfortunately is not what you want. Okay? If you take a look at frequency modulation, it's a little different. So with frequency modulation, if you remember what the equation was, we're just going to use AC is equal to 1 for now, just to make things a little easy. And then remember, you have your carrier, and then you are modulating the frequency, right? So remember, this was equal to the integral expression that we talked about before. Now, if you put it through your nonlinear system, and if you apply a bandpass filter to it, let's actually see what happens. Okay, so this bracket here is actually omega ct plus phi of t. So I guess there wasn't enough room to put that in, but that's what each of these are equal to. Okay, so you have this, and then this. Okay, so also the omega ct goes here, and it goes here as well. So when you apply this, okay, so you can apply the same operations that we did before. So you have AC cos omega ct plus whatever this is, and then you have cos squared. If you remember, cos squared was 1/2 plus 1/2 cos 2x. All right, so that's what's happening. Okay, so that's what you split it up, which is over here. Okay, and the x in this case is just, omega ct plus phi, which is what we get here. So the 2's carry over, and then it keeps going, and then it keeps going. And then you can collect, obviously, you can collect like terms. So this guy and this guy, oopsie, and all the way back. Sorry, let's see here, where am I? I think it was at 13, 15, oh, maybe 21. Oh, sorry, let's go back. I'm almost done here, actually, for this part anyway. Oh. Keep going, keep going. There we go. Sorry about that. Oop. Okay, that's not my doing. Now it's going by itself. Yep, okay, there we go. So we can group this one and this one together. Okay, so those go here. And then you can also group, so this one is by itself, which is over here. And then you keep going. So if you applied a bandpass filter, then what's going to happen is that everything else is going to filter out except for the middle. Okay? So when you do that, so you have your DC, so this is your DC term, right? So that's over here, right? Then you have your, you have your bandpass components centered at FC and then 2FC and so on. So if you apply your bandpass filter, all these three things go away except for this guy over here. And what's nice is that the output is simply just a scalar multiple of the original input. So if you take a look here, this is equal to 1. And then the output, when you do frequency modulation, is just a scaled version of the carrier, but the message signal stays the same if you actually compare them both. Okay? So the point to take home is that if you apply a nonlinear operation to a frequency modulated wave, then the output will actually not matter. So not matter, but the actual output will not be affected at all. So the only thing that's going to change is the height of the actual carrier, but the actual way you actually modulate the frequencies or change the frequencies in your frequency modulated wave will actually stay the same. So that's the point that I wanted to bring across. So if you apply a nonlinear device to a frequency modulated wave, you'll notice that the input messages are exactly the same. It's just the carriers change. So this is 1, and then that changes as well. So that doesn't actually change anything other than just the height of the carrier. Okay, so this is the last topic I'm going to talk about before we end and then do a tutorial. Should be very quick. There's got to be a way to generate FM signals. So what we talked about previously was just how to generate a narrowband frequency modulated signal, right? So we've only talked about that. But in general, you have any arbitrary signal usually has a wideband where the modulation index or the deviation index is very large. So there's got to be a way to generate any arbitrary FM signal you want. And what we're going to look at today is what's known as the indirect method. So what the indirect method does is that you generate first a narrowband signal and then you convert that into a wideband. There is the direct method, which is actually quite difficult, and I'm not going to talk about it here. You're not expected to know it, but if you want to take a look at the textbook, then you can certainly go ahead and look at that. But I'm just going to talk about the indirect method today. So how do we generate FM signals in general? So what the indirect method does is that you have your message, you generate a narrowband version first, and then you go ahead and make it wideband after by applying a couple of different techniques. Okay? So first step is to generate a narrowband FM signal. And that's very easy to do. So this is the equation. If you remember originally when beta was less than 0.3, this is the scheme that you would use to generate a narrowband frequency modulated signal. So what you need to do first is you have to first integrate your message. So that's what's happening right over here. And then there's a constant of KF, which is your sensitivity index, which we'll talk about later. So you first integrate, and then what you're going to do is you're going to take this and you're going to multiply by AC sine, which is what's going on right over here. So this and this are what's going on over here. So you have a cosine wave, and then you do a phase shift of minus pi over 2. So this is phase shifting. Okay, when you do this, so by 90 degrees. So when you do that, you get AC of sine. So this portion here, this here, is this part. So that's what's going on over here. Okay? And then what you'll do is you'll just take your carrier, AC cos, subtract the two values together, and then you get your narrowband frequency modulated wave. So that's how you do it first. You generate a narrowband frequency modulated wave first, and then you'll take this and make it wideband. So you want to convert this to wideband to make it more acceptable for transmission or for whatever medium that is going to accept this actual signal. All right? So step 2 requires what's known as frequency multiplier unit. So what that basically means is that you're going to take the frequency, the carrier frequency, or whatever the frequency is concentrated on for that narrow band, and you want to make it bigger by multiplying the actual frequencies. So how exactly does this work? So what people usually do is, if you remember way back, maybe about a couple of weeks ago, or maybe even 3 weeks ago, you take your signal and then you can apply some sort of nonlinear device. So you can either square the signal or take it to power 3 and so on and so forth. Okay, so if you do this, if you apply a nonlinear device, and then if you also put a bandpass filter around the thing that you want, right? So for example, if you were to do a cubed operation, oh no, not this shit again. Hold on a minute. Okay, give me one. I'm going to pause this again one more time. Resume. Okay, I'm just going to use the pen from now on. Okay, that's good. Okay, so if you remember how nonlinear devices work, you have to take the square to take the cube, and then what you're going to do is you can apply a bandpass filter around the the thing that you want to copy or the thing that you want to retain, and then the output would simply be your signal, but then it's modulated even further. So when you have some sort of signal that's coming in with the expected, so if this is the FM signal that's coming in, right? At some carrier frequency and at some frequency deviation, if you put it through a nonlinear device and then you apply a bandpass filter around the thing that you want, what's actually going to happen is that you'll get your carrier frequency multiplied by some amount n, which we'll figure out later, or whatever the thing that whatever the desired n that you want. But the point is here is that you just apply a bandpass. So you have a nonlinear device, and then you have a bandpass filter around where you actually want the actual thing to be. and then the output would simply be your signal that is modulated even further. So this just simply makes the carrier frequency and the deviation to be n times the amount. So if this is the input here, so this is the input, the desired would be this one. This is the output, which is fine. All right, so that's basically how you do the frequency multiplier. Okay, so let's take a look at let's take a look at second order for now. Let's actually take a look at what happens if you actually squared it instead. Instead of just, let's take a look at what happens if the operation was squared. Okay, so the output of this case here, so this is you are applying a squared term to it. Actually, so, fuck. Something wrong with my pen. Hold on a minute. Hold on a minute. Okay, sorry about that. So we're going to apply some non-linearity. Okay, so let's just assume that it's squared for now. Okay, so let's actually go through the motions here. So, so if you put in your frequency modulated wave, okay, so this would be cosine of omega ct plus. Okay, if you put this through, then what's going to happen is that you have some constant applied to the squared term. So that's what's happening over here, and then you want to apply a bandpass filter that is centered at whatever the order that is that you want. So in this case, because it's second order, you want to make n equal to 2. Okay? So if you do this, if you apply a squaring term and then put a bandpass filter at twice whatever the carrier frequency would be, so if you apply a bandpass filter here, what's going to happen is that this term goes away and what you're left with is this guy. So that would be the output here. Okay, so if a frequency multiplier is to put it through some sort of nonlinear device, in this case we're going to take a look at it in terms of the squared term, put a bandpass filter on twice whatever the frequency would be, and then the output is simply this. So if you actually take a look here, originally, my input, the original message was cosine omega ct plus, 5, right? And if you take a look here, I can actually factor out a 2 in this case. So I have a2 over 2, you have cosine 2, and then omega ct plus phi. Okay, so what's happening here is that you are taking your frequencies and actually you're multiplying it by twice the amount. So what's happening here is that the carrier frequency increases, also the deviation increases as well. Because if you remember, the deviation was equal to kf am, not am, but we'll just do m of p, right, over 2 pi. And if you multiply this by 2, that means the peak is also going to increase by 2 as well. So the deviation as well as the frequency, the actual carrier frequency is going to change as well. So that's actually what is happening. We'll just go to full screen. Okay, here we go. So, oh yeah. Okay. Sorry, hold on. Go full screen from now on. Okay, so the point here is that the carrier frequency and the deviations double. All right. So that's the point I wanted to bring across. So let's go back to the previous page. Oopsie. Oh, hold on a minute. All right. Okay, so this is the indirect method. All right, sorry, my laptop's on the fritz today. I don't know what's going on, but okay. So for single tone modulation, all right. So let's say our message signal was just single tone, and then if you put it through a frequency multiplier of some multiple n, and then you apply the right bandpass filter to the right location, then the modulation index will also multiply by n, which is nice. All right. Similarly, the carrier frequency as well will also multiply by n, but we'll talk about that later. So this is for single tone modulation. For baseband, if you want to use an arbitrary message signal, instead of f of m, you just replace it with b of m. Right, so this all changes. But the point of the frequency multiplier is that it will make your deviation increase by n-fold, depending whatever multiplier you use. You can use squaring, you can use cubing, it doesn't matter what you use. Okay, so increasing the deviation, right? So this is exactly what you need for wideband FM, right? Because remember, for narrowband, we're assuming that the modulation index is less than 0.3. If you want to make it wideband, what you have to do is you have to make this bigger than 0.3, and that's the point. So if you actually put your signal through a frequency multiplier, then the output goes from narrowband to wideband. So you're going from less than 0.3 to bigger than 0.3, which is actually what we want. All right? Okay. So in practice, very abrupt non-linearities can be generated. So you can actually go even further. Instead of going from 2 or 4, you can actually go very large. You can just go up to 1,000 if you want, right? So the point that I wanted to bring across is that the nth order frequency multiplier increases both the carrier frequency as well as the delta F, okay? But there's also, you know, there may be some cases where you don't want to increase the carrier frequency. What you may want to do is you want to increase the frequency deviation, but you want to make the carrier frequency a little smaller. You want to make it away from, you don't actually want to change the frequency deviation. You just want to change the carrier frequency itself. So there's another mechanism you can use, which is what's known as a frequency converter or mixer. So this is almost like the super heterodyne, where when you are multiplying two cosines of different frequencies, you'll have one that down converts and one that up converts, which is actually what we're going to do next year. Okay? Oh no. Okay, so let's see. So frequency converter or mixer. All right. So this is the next component that we actually need. Okay. So how this works is very simple. So you have some message that's coming in, and then you want to modulate, but you want to multiply by some, frequency omega naught, all right? So if you multiply by a cosine omega naught, then what you can do is you can apply a bandpass filter around the right thing that you want. So if you actually take a look, if when you're modulating, okay, you have two components here. So what's going to happen is that, you're modulating by, omega 0. So what's going to happen is that you'll have two components here. So you have 1 and then you have 2 because you're multiplying by this cosine wave. And then when you put a bandpass filter around the fundamental frequency that you want, so what's going to happen here is that you are basically taking your frequency components and you're either moving them up or moving them down by some frequency f of 0. Okay, so you're not actually multiplying, you're not actually adding, you're not multiplying the actual carrier frequency, you're actually changing the carrier frequencies so that they either go up or go down, but then the actual frequency deviations will stay the same. Okay, so we have two things at our disposal. All right, so we've got frequency multiplier units, so they increase both, the carrier frequency as well as the frequency deviation. Right, so when you increase the frequency, the frequency deviation, it also increases the modulation index or the deviation index if you want. For frequency converters or mixers, you only increase or decrease the carrier frequency only. You don't actually change the frequency deviation, which is what we want. Okay, so you have a bunch of these units together that go from narrowband to wideband. So if you configure these in such a way where you put them together and they interconnect in some way, you can actually achieve going from narrowband to wideband. So you're going to use multiple units of these to get what you want. So here's a quick example. All right, so first off, we have some message signal. We're going to use a narrowband frequency modulator. We're going to make sure that the the deviation is less than 0.3. Okay, you're going to apply a frequency multiplier first, and then you're going to use a mixer. In this case, it's what's known as a down mixer. All right, so a down mixer, what that means is that you are taking your frequency and you're shifting it downwards instead of upwards. It's also what's known as down conversion too. All right, so, oh yeah, it works. Down conversion. So it's also what's known as down conversion, because what you're doing is that you are taking your frequency and moving it down. Okay, so we have a narrowband frequency modulator that has a carrier frequency of 0.1 megahertz and a deviation of 20 hertz. So this belongs to this guy over here. Okay, and then you have a wideband frequency modulator. That's the desired output. So whatever is out here, this is what we want. We want to make it so that the carrier frequency is 100 megahertz and the deviation for the wideband is 75. So we have to figure out the right numbers. We have to figure out the right multiples, N1 and N2. As well as, actually we just have to figure out these numbers, what these are. So what are these? So we have to determine. So need to determine. Okay, so that's actually what we have to figure out. So we have to figure out the right numbers, N1 and N2, that will actually give us the desired carrier frequency and the deviation. And we also have a mixer frequency of 9.5 megahertz as well. Okay, so this is what the narrowband frequency modulator looks like. That's very standard. We've seen this already, right? So you're just integrating the message, apply, AC sine, and then subtract it with AC cos, and then that's what you get. All right. Now let's actually check if the narrowband frequency modulation condition is satisfied. So you have to make sure that the beta is less than 0.3. So that's actually pretty simple to do. Okay, so the message, if you remember, actually the message is band limited between 100 and 15 kilohertz. So that was the requirement. That was actually the requirement of the question. So the message signal varies between 100 to 15 kilohertz. So if you want to figure out whether or not the modulation index is satisfied, all you have to do is remember that the modulation index is delta f over f of m. Okay, and this varies between 10 and 15 kilohertz. Okay, so 10 and 15. Okay, so let me see here. So we have this is our frequency deviation. It's simply 20 hertz. Okay, if I divide by 15,000, this is the largest value that we have. This is actually equal to 0.001333 or so. So it's actually very small. And then the worst case is when you have, actually it's 100 hertz, not 10, sorry. When you divide by 10, you get 0.2. So this is less than 0.3, so we're actually okay. Okay, so that is satisfied for sure. 7. All right. So this is the worst case scenario. So the range of frequencies, or not range of frequencies, the range of deviations will go from 0.013 whatever to 0.2, which is great. Okay. All right. So this is the process. So we have to go from narrowband to wideband. So how exactly does this work? So what we're going to do is we're going to solve this generically in terms of n, and then we'll figure out what the actual numbers are very soon. Okay? So going from narrowband here, right? This is a narrowband frequency modulated signal, FM. FM. So remember, frequency mixing only changes the carrier frequency. It doesn't change the actual deviation, which is what we're looking for. Okay? So what we have to go from here, so we're going from the beginning to the end. So remember, the mixer doesn't change the, it doesn't change the multiplication factor, right? So the overall multiplication factor, right? So we're going from n1 to n2. So when you put it through here, you're going to multiply by n1, all right? And then you're going to go through this again, multiply by n2, and that's what happens here. So the whole total the whole factor here, when you're multiplying, the total factor is n1 times n2, okay? So the overall frequency multiplication factor is determined by this guy here, and what you want to make sure is that the frequency deviation for wideband is n1 times n2 times the narrowband. Okay? So this is what we actually want to do. So we have to figure out some combination of n1 and n2 that will actually give us this wideband here. So remember, when you put your signal through, you're going to multiply by n1. This doesn't affect anything. This doesn't affect the multiplication. The mixer doesn't. And then you're going to put it through n2 again, and then that's what we get. So this is, this is what that relationship means. Okay, so let's actually go through this. So let's see here. So n1, n2 is divided. This is what it's defined as. So this wideband here, this is from the question here. So we desire a frequency deviation of 75K, and the narrowband modulator gave us 20. So the total frequency multiplication factor that we need is going to be 3750. So going from the beginning to the end, we have to make sure that we have multiplication units that will make it so that the final multiplication is going to be 3750. All right? So let's actually go through the pipeline here in a little more detail. So this is this stage here. So we have a narrowband frequency modulator with some frequency deviation and some carrier frequency, and then when we put it through the frequency multiplier, right, what's going to happen is that each of these values are going to be multiplied by n of 1. So this here is not subtraction. Don't confuse this. This is the carrier frequency for narrowband frequency modulation. So that's what that is. So it's not f of c minus nb. It's f sub c dash nb. So it's a little confusing here. But the point is that you take both of these and you just multiply by n of 1, which is good. Okay. Now, this here is a down converter. Okay, so what that means is that you're going to take the frequency that's coming in, and then you're going to subtract and down convert. So you're making it less. Okay, so this is before the mixer. After the mixer, you notice that the deviation stays the same, but the carrier frequency is going to change. So f of 0 is over here. You're going to take this and subtract with whatever the frequency is coming in. So remember, you have your components that are centered at the carrier frequency f of c, right? So when you put it through a mixer, you're going to change it so that you're shifting it down by whatever F0 is defined as. So it's going to be F0 subtract whatever the incoming is. So the carrier frequency stays the same, but the delta, the deviation doesn't. Sorry, the deviation stays the same, but the carrier frequency doesn't. That's what's going to change. So the mixer does not alter the deviation as I talked about, but the down mixer will certainly change the carrier frequency. It actually brings it down. All right. So at this point here, what's going to happen is that you're going to take this guy and then you're going to multiply this by n of 2, which is what's going on here. So the n of 2 is actually carrying into both. That's what happens here. And then notice that the frequency deviation also stays the same. So this is what n of 2 is. So when you actually run through this whole pipeline, right, what's going to happen is that the total deviation that we get is going to be n2 times n1 times the narrowband deviation, right? Because when you put it through the mixer, it doesn't change the deviation, but it changes the carrier frequency. So this is the desired result. So I have two conditions here that I need to satisfy. Okay, so the first condition is the wideband deviation is simply equal to this, all right? And the wideband carrier frequency is simply equal to that. Okay, so I have two conditions that I have to solve for. So these are what are known as the design equations, because you have to figure out the right values of n2 and n1 that'll satisfy these equations, and it's actually pretty simple. Okay, here. All right, so those are my design equations. That's fine, right? So I just took these guys and brought them over, which makes sense. So what I'm going to do now is very simple here. So this, I'm just doing some substitution. So this is equal to 20, right? This is equal to 75K. This is from before, right? This is equal to 9.5 megahertz, all right? And this is equal to 100 megahertz, all right? And this here, let me see here, so 0.1, yeah, here, oh shit, not again. Sorry, screwed up again. Let me go back up, full screen. Sorry, let me just pause this here quickly. Okay, so that's 100 megahertz. So what's going to happen is that you have these equations here, because this f of c and b is equal to 0.1. So let me just, okay. Trying to see where exactly, oops. So this here, right, is equal to 0.1. So this is 0.1 megahertz. Okay? So that's what's happening over here. So if you do all these substitutions, right, what will happen here is that we know here, if you solve this, n2, n1 is equal to 3750. So if you take this and you substitute it over here and you solve for everything, what will happen is that you'll get two values of n1 and n2. So you get 75 and 50. So that's actually how you solve it. So in this case, n1 will equal 75 and n2 will equal to 50. Okay, so those are the equations that you actually take a look at. Okay, so let's actually run through this to make sure that this actually works out. Okay, so we had our deviation of 20 hertz, all right, and then our carrier frequency was 100 kilohertz, or 0.1 megahertz, all right. After you run through the first multiplication, okay, so we're timesing this 75 and timesing this by 75, we see that the deviation is going to be 1.5 kilohertz or 1500, and then if you multiply by 75, you get 7.5 megahertz here. Once you run through the mixer, you're going to take 9.5 subtract 7.5, right? So that's what's happening here. So that's what the equation is doing here. We get 2. So this is 9.5 subtract 7.5, right? Because this is f0 minus 7.5, and that's what you get. The deviation doesn't change, okay? And then when you run it through the second multiplier again, you're going to multiply this by 50, and then this is what you get. So remember, the design specs told us that we want the desired output to be 75K for the delta F, and the carrier frequency is going to be 100 megahertz. And that makes sense. We've satisfied it. So the design targets have been met. Okay, so this is the last topic, and then we'll take a break. I'm going to do the tutorial. So we're going to talk about how exactly you would demodulate FM signals. You can actually do this through using a PLL, or phase lock loop. Okay, so how do we demodulate frequency modulated signals? So if you remember from the past, we talked about this. A phase lock loop is used for tracking the frequency of an input signal. So we talked about how we can use PLLs for demodulating AM signals. You can also use a phase lock loop to demodulate FM signals as well. Okay, so it's for locking or tracking changes in the instantaneous frequency of the incoming signal, right? It's also used for narrowband filtering. You can also use it for frequency synthesis if you want, but I'm not going to talk about that here. Okay, so this property here, if you're locking and tracking changes of the instantaneous frequency, this is used for FM demodulation, which is going to be nice. All right. So if you remember briefly, right, this is the structure of a phase lock loop. Okay, the phase lock loop looks like the following. So, oh God, let's see here. Where's my toolbars? Standard. Just get the eraser out. Okay, that's good. All right. So if you remember what the phase lock loop looks like, all right. So how this works is that you have a phase detector, and then what the phase detector does is that it checks to see, you know, how much of a difference there is in phase, and then you have a loop filter, and the point of all this is to have some sort of error signal. So what that error signal does is that it figures out the difference between the frequency that is coming in and the local oscillator frequency that is generated in the phase lock loop. And whatever that error signal would be, it's used to lock on so that it will generate a frequency that is of the same frequency that is coming into the phase lock loop. So the instantaneous frequency in this case, if you actually take a look, so remember, this is our input that's coming in, right? So the instantaneous frequency here, right? So what's going to happen is that you have your cosine that's coming in, and then if you remember for the phase lock loop, the output, you have some sort of output frequency, and then remember this is a phase shift, which is sine. So if you take a look here, the instantaneous frequency, if you remember, is just 1 over 2 pi, whatever the derivative of this is here, okay? And then you have, so if you remember, this is equal to, you know, you have some, you know, factor 2 pi here. But the point of this is that the error signal here, if you actually use this, it's directly related to the instantaneous frequency of the output. So that's, if you actually, you can actually use this to actually demodulate FM signals. Okay, so or equivalent, oh shit. Hold on a minute. It just crapped out a minute. Okay, sorry about that. Sorry, let me just unplug this, plug this back in. Sorry about that. It just knocked itself out. But, okay. Come on. Almost done here. Okay. But the point here is that, you know, this is the instantaneous frequency. If you want to get back the original message, you just integrate. And this is the point is here. So what exactly does this actually mean? So if the inputs, so this is the input signal that's coming in, right? Remember, you have your frequency modulated wave, and this is what the message signal would be. And then you have a free running frequency, which is set to the carrier frequency of the frequency modulated signal. Okay, so you want to make sure that you set the local oscillator to match whatever the carrier frequency would be. Okay, so how exactly does the phase lock loop operate? So remember, how the phase lock loop operates is that you are trying to lock on to the instantaneous frequency. So whatever the frequency that is coming into the phase lock loop, you want to make sure that the local oscillator matches whatever the incoming frequency or the incoming time varying phase would be. All right, so let's see here. So this is the input, right? So the input is your frequency modulated wave. And then the output is going to be the same thing. Because remember, what you're doing is you want to make sure that the frequency modulated wave, you want to make sure that the output and the input track each other, or they're basically the same. You want to make sure that the local oscillator tracks onto whatever the, you know, whatever the input frequency is coming in. Okay? So if this is the input and this is the output, so notice that basically these are pretty much the same. Okay? So what you can do is you can just make the error signal, whatever the error signal coming out, that's the actual message signal itself. So what you can do is you can actually use the error signal of the PLL to actually demodulate your actual signals. Okay, so that's actually what the whole point of the phase lock loop is. You can actually use it directly. So therefore, you can use the PLL that is tuned at the carrier frequency to demodulate FM signals. So you actually don't use this guy. You use the actual error signal. So this is VE of T. Okay, so you actually use the error signal to actually demodulate your FM signals instead. All right, so that's something that you want to take into account. So, okay, so there are other ways you can demodulate FM signals, right? For example, you can use envelope detection if you want. So, you know, what you can do is you can just put a bandpass filter. You can take the derivative, put an envelope detector, and then you put a DC block. So what's happening here? So let's just, you know, do this for a moment. If you took the derivative of your FM signal, what's going to happen is that, this is very simple. So this is just basically chain rule. So when you take the derivative, right, what's going to happen is that the derivative of, the message signal over here, right? So remember, if you're doing the chain rule, so if you have cos of, x of t, for example, if you took the derivative, you'll have x prime minus sine of x of t, right? And then in this case, x of t would be equal to this guy over here. So when you do this, this is what you get, right? So when you take the derivative, this is what happens here. And then this is an envelope where the carrier frequency is going to be bigger than, the magnitude of your message. So put a bandpass filter first to make sure that you're isolating everything. Take the derivative and then do an envelope detector and do a DC block. So what you're doing is you're actually getting rid of this guy here, okay? And then what's going to happen is that you're just left with the message signal itself, which is multiplied by some gain. And that's it. Okay, so that's all I have for FM signals. We're going to take a little break. I wanted to end sooner, obviously, but my pen kept on crapping out. So take a little bit of a break, come back. I'll do some super heterodyne questions, and then we'll get out of here for the day. So thanks for coming.